Actually, you're okay there. I'm going to just talk about from this mic. I'll come back and take the head mic a bit later, but you can relax for 2 minutes. But maybe if you can put on some nice activating music, very loud, so we can encourage everybody to come inside, that would be marvelous. Choose anything you like, just some very loud music to wake up the rest. Thank you. Thank you, everyone. Thank you. Thank you. Thank you for being back in the room and on time. I do want to try and get started because we're already almost 5 minutes over and I want to not take any more time from our main speakers. This section is ISRU Surface Operations Part 2, and Robert Lindner, who's been on stage a lot in the last couple of days, actually. It's a good thing, Robert, we have your expertise. And you will be moderating this event. As always, welcome back to those online and send your questions through the chat.
Thank you very much. Test. Am I? Yes. Okay. Thank you. So we will start this session with Stephen Kai from GMV, who's going to give us a talk about Lupin, enabling high-performance PNT in a lunar environment for rover surface operations. Stephen, the stage is yours.
Okay, thank you and good afternoon. This afternoon I'm going to be talking about PNT, so position, navigation and timing, in the context of lunar operations for specifically rovers. This is a NAVIS activity funded by the European Space Agency, primed by GMV, and also with quite an interdisciplinary team from the GMV group representing the activity. So what I'm going to talk today about is give you a bit of an introduction for the activity that we're performing. I'll introduce some of the use case analysis, and finally the selection of use cases that we're focusing on for the activity. Then I'll discuss a little bit on the architecture perspective, on how we can architect a PNT solution for rover operations for future platforms. Then talk a little bit about the rover that we're actually going to be deploying this in for an analog field test campaign, and then finish with the forward prospectus on what the upcoming work shall be. So the objectives of this study, again funded by the NAVIS program in ESA, is to study the current state-of-the-art planetary PNT techniques, specifically from what they call the user perspective or the user segment. So for rover operations, for human exploration in the future, and also from there to define, develop, and demonstrate in representative analog tests the solution that we come up with, and how the PNT solution, or the position, navigation, and timing solution, can be combined with conventional rover navigation solutions, such as visual, inertial, or celestial, which have been quite matured over the years, and how we can tune these systems for different use cases or different areas of the lunar surface based on what the mission calls for. And then lastly, the idea is to provide a detailed assessment of the tangible benefits that having the PNT enabled or the PNT based navigation solution can give to the user segment, specifically in the rover perspective, but also for landers and again, human exploration in the future. Just a quick note, the Lupin project is formed of GMV UK acting as prime contractor. We have two sections from GMV. We have the onboard GNSS team from the Guidance, Navigation and Control Division, and then the team I represent from the UK in the Robotics and Onboard Autonomy Division. We also have GMV Romania acting as subcontractor, providing support for the onboard software. So quickly looking at some of the use cases, there's quite a number of interesting use cases that we can use or that we can look at for having PNT available on the lunar surface. The activity is focusing really on the sensor fusion aspects to achieve a high accuracy PNT solution, which is fusing the LCNS signals which are coming out of the development of the Moonlight program. LCNS standing for the Lunar Communication and Navigation Satellites, which will be initially a service providing mainly navigation and communication services around the South Pole of the lunar surface, but then in the future may expand to provide other areas coverage as well. A lot of the use cases that we identify in the activity and prioritizing the activity are located in the South Pole region because it is the area of most scientific interest currently, and it has the greatest coverage of LCNS planned. This also includes permanently shaded regions, and also another benefit of having South Pole coverage is that we can also have from past orbiter missions such as LRO, very high resolution detailed elevation, digital elevation models or DEMs that we can also use as an input to our PNT solution here as well as a measurement. So you can see in red the ones we've highlighted are the ones that we're prioritizing for testing. So this includes lunar fast rovers. I'll touch on this a little bit later, but it's effectively pushing beyond what the presentation I gave this morning was talking about for EMRS, looking at future concepts of driving up to maybe 1 meter or past 1 meter per second on the surface. Then the typical ones being farside operations, PSR operations, static surface operations, and South Pole operations using or not using DEM inputs as well. So in terms of the architecture, we've defined at sort of design level a flight concept that takes into account a number of measurements from various sensors conventionally found on rovers, and also to be introduced through the introduction of LCNS through the Moonlight program. We have to take an approach here which is based on sensor fusion because the number of LCNS space segment satellites will be limited, meaning that our precision and accuracy will be not that we see from GNSS or GPS on Earth. We need to fuse, this implies therefore we need to make a sensor fusion based solution which takes LCNS and also potentially GNSS signals from the Earth, which are reflected from the surface. And using high sensitivity receivers, we can combine them into the solution as well. From the rover perspective, we take the traditional sensors of IMU for inertial navigation. We fuse this with a visual component, in this case visual odometry over SLAM, or simultaneous localization and mapping. And we also add in the absolute orientation or absolute heading measurement from a star tracker as well in this case. This is chosen over sun determination using navigation cameras or indeed sun sensors. As I mentioned, in addition to the LCNS signals, we also take the GNSS component with the reflected signals from Earth, and specifically the side lobe signals that we can include a high sensitivity receiver, which is already in development for the lunar surface, and we can factor this into our architecture as well. The PNT engine itself, so the processor which will be responsible for the sensor fusion, is based on an extended Kalman filter model, and takes in the measurements that I've just described. So from inertial measurement units, from visual odometry, from LCNS signals, which have to be, in this case, simulated, and the GNSS. One of the key aspects of this activity for us is that we need to map real GNSS measurements in field trial conditions and simulate LCNS condition measurements in order to create a representative PNT engine and also a representative use case for the demonstrations of the test. So on the right, you can see kind of how this fits onto the rover. We have navigation cameras, which provide us with local path planning in front of the rover. We have localization cameras, which are providing us with the visual odometry inputs. We have celestial navigation, which in this case, we will be simulating using ground truth measurements. We have the option of including wheel odometry if we wish to do so, and then inertial measurements as well. And then an antenna focused for the GNSS and an antenna for the LCNS. Moving on, talking about the lunar simulation component, we have to develop from scratch a lunar simulation tool effectively, which is responsible for streaming the real-time RF measurements to the PNT engine from the sensors that we have on Earth. Effectively, what this creates is the ability for us to simulate a lunar rover where the rover thinks it's driving on the moon, but actually we're using Earth GNSS signals for it to do so. To do this, we have a component that we're building that will effectively map the RTK fix, or the GPS fix of the rover, to the moon's surface. But critically, we can do so in a way which allows us to select the region of interest for the use case that we're under test. It also allows us to simulate the LCNS measurement and the clock ephemeриdes from the GNSS measurements that we're receiving from the rover. And then lastly, we can map these GNSS measurements that we have to the lunar surface as though they were the reflected signals as well. In terms of the rover platform, we're reusing one of the platforms we have in GMV from a previous activity called Rapid. It's a 4-wheel skid steer platform you can see up on the top right. It's actually our fast rover platform, so with this, it goes beyond what EMRS is capable of in terms of speed and can drive at speeds of up to 1 meter per second in test campaigns, which gives us a lot more scope for fast lunar navigation and also building the GNC, if you like, the guidance, navigation, and control, which go on top of that. So for this activity, we're taking an existing GNC that we have from the Rapid project and from another activity called FastNav, which includes local and global planning based on fast marching, trajectory control, which is based on the pure pursuit method, and a component we're developing in another activity called FASTER, which is based on artificial potential fields, so where you do not do path planning and you save the resources on board the rover by effectively dragging the rover to the goal location by an artificial force and repelling it using repelling it from the observed obstacles in the environment. As part of the activity for Lupin, we're also upgrading the rover platform you see here to make it to increase the endurance of the platform. To do this, we're adding additional batteries and the ability to hot swap the platform batteries during the test campaigns. And then also to allow us to operate in dark and shadowed areas, we're including navigation lighting on board as well. In this, we can save power by flashing the lights on and off as we want to capture camera frames during the test campaigns. The software deployment that we follow on board the rovers follows what's called a containerized approach. So for this, it means we have the same development, deployment, and testing environments. It gives us a lot more stability during our developments. These Docker containers will be deployed on board the rover, and on top of that, we will have the PNT engine that I've just shown, and also the Lucem components. They're developed in MATLAB Simulink natively, but we will take a auto-coding approach to compile them down into C, and then take that source code, or that source code, convert it to a library, and then harness it inside the framework that we use for robotics called ROS2. Ultimately, this will be deployed onto a second platform PC, so an UltraScale Plus over here, which we refer to as the anime breadboard, and then that will be connected to the rover platform's typical onboard processor or onboard computer. As I mentioned before, for the celestial navigation, because obviously we'll be working in a combination of daylight and nighttime, what we'll do is take the ground truth measurements from a GPS compassing device, and we'll apply a model to bias and apply the characteristics for a typical star tracker to give us the absolute heading or knowledge that we need to feed into the sensor fusion model for the test campaign. In terms of the test campaign itself, we're planning an extensive field trial. Oops. Someone's changing the slides. We're planning an extensive analog field test campaign in the Fuerteventura in the early 2025 or in February time. The test case definition for this is not yet finalized. However, the use cases that we've identified and prioritized are driving and dictating the scenarios that we will be testing during the campaign. And with this field test, we aim to test out various different configurations of the PNT engine, so with and without GNSS, LCNS, with and without visual odometry, etc. We also have test campaigns which cover nighttime and daytime operations, and this covers both low inclination artificial light from theater lighting, and indeed complete darkness as well. The idea for the activity is required by ESA is to have test campaigns or tests which are able to last for up to 6 hours of continuous operation. In terms of upcoming work, I'd like to reiterate that looping is an activity funded by ESA through the NAVIS program. We're currently preparing for the critical design review, which is due in mid-May. Following this, we'll be implementing the sensor fusion model that I've described, and then deploying it onto the rover with the rover guidance by the end of Q3 this year, ready for Q4. And then from there, we'll be planning the analog field test in January, February next year. And hopefully with project closure shortly following that. And with that, I'd like to close here. There's a link up here to the ESA page for NAVIS, which gives you more information on the activity, or indeed feel free to contact me on that. Thank you.
Thank you very much. Are there any questions? Is everybody digesting, or are you still with us? I hope so, yes. Okay, so you can think about the question. Maybe I have one for you. Okay. I might not have captured it, but if you do visual navigation as well, I mean, you're fusing these different kind of information, celestial information, kind of sort of GPS. The lighting conditions, what is the impact of the lighting conditions?
On the visual navigation, potentially massive. So that's why we include the artificial illumination. And I maybe didn't cover it particularly well because I was rushing towards the end, but the idea is that when you're driving in a shadowed area particularly, or indeed complete darkness in a PSR, what you can do is flash the illumination so that you're not consuming continuous power by having the lighting on all the time. And you can do this, you can trigger the cameras in a sort of consistent way with the lighting so that you can accumulate the images. And for VO, when you're looking sort of in the short near field, all you need is enough rich features in that local environment. But for sure, there's other things that you could do on top of that. So you could take account for the lighting condition to try and reject the shadows, for example, in the VO solution to make that solution better, for sure. But it is a constant problem with visual odometry, even on Earth and in sort of terrestrial systems, that it is subject to lighting.
Exactly, and comparing different frames, for instance, if you take images, you compare the different frames, you may see the difference and take the relative.
Frame to frame is the problem. The left and right frames are okay because they're synchronized. But the interframe matching is where the error is introduced, and for that you need to reject a lot of outliers, and then, as I mentioned, deal with orientation of shadows or something like this, like a model-based tracking. Effectively, you can introduce other concepts that will improve the performance.
Okay, thank you very much. Still an opportunity for a question. If there is none, I don't see any. Then I would like, thank you very much again. Just put it there. So, next speaker, sorry, I have my wrong glasses on. We have now Matt Cross, and he will tell us something about supporting and advancing operations of lunar surface infrastructure through autonomy. The floor is yours.
Great, thanks very much. It's exciting to be back here at Space Resources Week for this is my third time here. And so yeah, I just want to start off by presenting who we are at Mission Control. So at Mission Control, our focus is on developing software solutions for Earth, Moon, and Mars, and really from the perspective of the human operators sitting on Earth in the operations center. And so we are supporting the operations through two core product offerings. So our first is our Spacefarer Mission Operations Software Suite. So this is a web-based operations platform for enabling remote and distributed operations for payloads, robotic systems, and potentially other lunar infrastructure elements. And our Spacefarer software has been tested in thousands of hours of analog missions, and we're excited to say that it'll be used for supporting upcoming lunar missions. And then we are also heavily involved in AI and autonomy applications, and specifically in deploying AI models to spaceflight hardware. So our Spacefarer AI deployment toolkit has been developed to support deploying AI models to spaceflight systems. And we've had two successful deployments to spaceflight hardware and demonstrated last year. And just sort of wrapping up what are some recent success at our company is we have made a number of commercial sales in both the software as well as selling some edge compute, space-like computing solutions. So we know that, so as a company focused on operations and thinking about challenges from the perspective of the human operator on Earth, we know that there's a number of challenges with respect to lunar infrastructure operations. So there's a limited a priori knowledge of the exact surface site location. So there's plenty of remote sensing data, but how you perceive that environment is going to be different once you actually get down to the surface. Operators and operations will experience latency, limited bandwidth in communications, and then of course, depending on communication architectures, communication blackouts. And then we know that for upcoming and recent missions to the lunar surface, there's still quite a dependency on human operators. And so as the complexity of those missions increases, there's going to be an increase in cognitive loading on those human operators. And with increased cognitive loading, there's the potential for missed opportunities, for example, in identifying opportunistic science targets. And this also poses challenges in scaling up operations. So it is well understood that AI and autonomy will be required for supporting operations of lunar infrastructure elements in the future. Both, we know that there's going to be large volumes of data generated and collected on the surface, and so AI and autonomy will help be able to process that data at the edge, prioritize that data for downlink. And ultimately for human operator consumption for that key decision making. Autonomy and AI is going to help robotic systems situate themselves in their environment by localizing themselves, as well as potential targets of interest or obstacles. And then, of course, as U.S. systems and missions are increasingly going towards excavation and beneficiation and other in situ resource utilization missions, those robotic systems will need to be able to interact with that environment. So understanding that environment will increasingly need to be more of an autonomous approach. And so ultimately there's significant challenges in operations that autonomy will be able to support. And so to that end, we are focusing on the building blocks in order to reach those further stages in complex autonomous operations. And so in this past year, we had 2 successful flight demonstrations of our Spacefarer AI deployment toolkit. So the first was our Lunar AI capability demonstration, in which we were a payload customer on the iSpace M1 mission. And that was our MoonNet payload, which is a segmentation network for terrain classification. And I'll talking more about that in the coming slides. And then more recently, we had a successful campaign with ESA's OPSAT platform, in which we demonstrated hybridized deployment of a deep learning model to both a spaceflight CPU and FPGA implementation. And so both of these demonstrations have increased our internal capacity and capabilities in deploying AI models to spaceflight hardware, and just continues to grow our expertise in this area. So our Lunar AI experiment, or MoonNet, was manifested on the iSpace M1 mission. And so our MoonNet model was a lightweight semantic segmentation convolutional neural network with the intention to perform terrain classification at the lunar surface. And so this was a lightweight model deployed to a Xiphos Q7, which is a spaceflight rated edge compute node. And the overall intention was for the payload to perform image segmentation and terrain classification on images collected from the Emirates lunar mission rover, Rashid. And then the resultant data products would be downlinked to the ground visualized in our Spacefarer Operations Science Visualization Suite to support the ongoing rover operations. And so I do want to highlight that this was supported by the Canadian Space Agency's LEAP Capability Demonstration Program, and so we acknowledge their funding. And so also manifested on iSpace M1 was the Emirates Lunar Mission Rashid rover, and so I do want to also acknowledge MBRC's contribution to this AI experiment. So how this experiment was intended to work was the rover would be driving along the surface and acquiring images with input from the science operations group, of which I was one of the members. And so as it would capture images, those images would be downlinked to Earth via the lander, which is where our payload was hosted. And so our payload would then perform image segmentation on those images, and then the resultant data products would be downlinked to the surface, and then we could use our science operations interface for visualizing both the raw image and then the resultant segmentation mask overlaid. And this was used for, or the intention was to be used for informing and providing guidance to the science users for future or what the next steps would be for the operations. And one of the key challenges was that MoonNet, as it was developed, was expected to not be, perform or be very performant. And the reason was, as noted before, the mission was going to a location in which there was no a priori images taken. So we had to do our training on our model using images captured in our own internal Moonyard facility. But we wanted the ability to update that model in flight during the mission. So the software payload was developed to support up to 2 in-flight updates based on images collected during the surface operations. And so we developed an entire machine learning operations pipeline for supporting the acquiring new images, labeling, training, and then eventually staging a new model for uplink to the payload model. And so this was a large effort that involved numerous workshops, rehearsals, training, to really refine that operations process for how we do in-flight updates of machine learning models and other deep learning models. So this was unfortunately, even though the iSpace M1 lander did not successfully soft land on the surface, this was still a huge success, and we achieved a number of significant milestones along the way. And so as far as we understand, MoonNet was the first deployment of a deep learning model for lunar surface operations. We tested and validated our pipeline for training and deploying deep learning models to spaceflight CPUs. We confirmed the functionality of our payload in both deep space flight as well as in lunar orbit. And we developed the ground infrastructure and operations and set that up to be ready for supporting 2 in-flight software updates. And so even though we did not get to do the full demonstration on the surface, we're still quite proud of our successes. And we can say that MoonNet is indeed on the surface. But unfortunately, we couldn't do the full demonstration. Some other recent activities involved in the area of federated learning. So federated learning is a process by which machine learning and training can be done across distributed computer networks as opposed to requiring all the data to be transferred back to a central location. And so this has use cases on the lunar surface where there may be large volumes of data generated on the surface, and not all of that data can be sent back to Earth over limited bandwidth. And so we did a demonstration in which we trained our MoonNet model in a distributed fashion across some distributed edge computing nodes, and so we see this as a promising solution. So moving over into the supporting of operations side, so our Spacefarer operations suite, we're developing for full mission lifecycle support. So if you are beginning to develop breadboard models of instruments or spaceflight systems, now is the time to start thinking about how you'll interact and operate those systems. And so the intention behind Spacefarer is to get it in front of users during breadboard testing, during prototype development, during analog operations, and then it'll be the same system used for actual lunar surface operations. And so we've been using this. It's been used for thousands of hours of ground testing and analog missions on Earth. We also run an education and outreach campaign with this software, and we are excited to say that it will be supporting upcoming missions to the moon. All of this work is done using our indoor moon yard facility. So it's indoor 30 by 20 meter lunar test bed, which we can reconfigure depending on the use case. And so we use this facility for developing our training sets for our MoonNet model, and we'll also use it for high fidelity lunar operations and training and testing, and where we conduct our educational outreach activities. We also have robotic arms, which we use to validate that our operations software can interact with different types of robotic systems, and also using it for developing training sets for robotic systems. Some upcoming work is the Aardvark campaign, which is a NASA P-STAR funded program for robotic precursor mission for collecting data as a robotic precursor, so that when astronauts return, they can have that data available for visualization in an augmented reality setting. So we're supporting the field campaign later this fall, and as well as supporting the concepts of operations development. So where is all this going? So we know that operations are going to be key to future lunar missions and lunar infrastructure development. There's lots of opportunities for developing autonomous systems, and some of the key barriers to deploying those autonomous systems involve deploying those AI models to edge computing. And so we have been learning those lessons and being able to address those challenges. And so we look forward to hearing from the community. If you have challenges that you need solutions to, feel free to come talk to us. And so thank you very much, and yeah, I'm happy to take questions.
Great talk, thanks very much. Are there any questions in the audience? Please wave, it's hard to see you. I see a lot of people are waving. Where are they? No? Well, then maybe you allow a question from my side. The currently available space-qualified, say, CPUs and computing capabilities, as to how are they, let's say, sufficient to what you intend to do and what you're doing, and what are your requirements in this respect? What would you like to have, let's say, on board?
That's a very interesting question. So our approach is to develop our AI solutions to what is available. And that it does impose a number of challenges. So, like, for example, our MoonNet model had to be a very small scale neural network in comparison to what you would have for like terrestrial applications. And so our intention is to, like, as the space qualified computing grows, then we're looking to grow with that development. But also not just focusing on CPUs, but as spaceflight rated FPGAs become more widely available, and GPUs, for example. So we're intending to sort of grow with the available platforms.
So by applying, let's say, several GPUs, for instance, you could, let's say, implement more and more elaborate, let's say, deep learning models.
Oh, absolutely, yes. Yeah.
Okay, yeah. Well, that's maybe something to push for in the future. Okay, thanks a lot again. Great talk. So the last, obviously not least from this session, is now Mr. Tristan Schnell from Forschungszentrum Informatik, and he will tell us something about talking about autonomous robot teams, scalable automation for in-situ resource utilization.
Yeah, let's just say autonomy for now, and we'll figure the rest out as we go along.
Okay.
All right. Yeah, hi from my end while I'm waiting for the presentation to come up. My name is Tristan Schnell. I work at the FZI. We're doing a lot of different research, especially autonomy, but before we start with that, maybe I should get a little bit into who we are. Many people here know us because of that, as the people that won the challenge, the ISRU challenge, the Space Resources Challenge, let me say it like that, or otherwise were crazy enough to put an angle grinder onto an autonomous robot. But in general, we are a research institute that's doing a lot of different research in computer science. We are based on South Germany, Karlsruhe specifically, and we are doing research transfer, which means, in a way, we're taking research out of academia and trying to actually push this into industrial applications and working closely with companies. Or a little bit differently, to use Catherine's graph, we're kind of there, like right at the edge between research and industry and trying to help both. Just some numbers, so you have seen them, because I'm probably going to get in trouble if I don't show them. We are quite big for a research institute, but that's for all of computer science. Our robotics group is like 25 to 30 full-time researchers, depending on when you look at it, and a lot of students that help out. Also important to note, we are non-profit. So we are only funding ourselves with the projects and not creating any actual profits, and also not creating any products, which is interesting to know if you want to work with us. So more doing prototype studies and stuff like that. The field of robotics that we're targeting is pretty much everything you can think of. We're doing robotic hardware, drivers for robotic hardware, and a lot of enabling technologies, like navigation, stuff like that. Maybe more interesting here is we have by now quite a big space heritage. We're doing many, many different space research projects, mostly funded by the German Space Agency, but we have some international projects by now as well, targeting everything from satellite assembly to mobile autonomous robots, which is why I'm here, and even stuff like actually deploying AI in space. Now, I promised to talk about robot autonomy. For us, autonomy is something we're trying to use in pretty much every field of robotic where we can find use for it. Important fields for that are, for example, logistics and inspection scenarios in the industry, but also some little bit more esoteric, let's say, things like healthcare robotics. There you can see on the right image an actual robot of ours deployed in a real hospital helping people. All of these come with different challenges, and that obviously also goes for autonomy in space. So we've heard a lot about why we want many, many robots in space by many different people. I've seen so many beautiful renderings of hundreds of robots working together in space. But the question is, how do we actually get there? And to really deploy autonomy in complex and potentially dangerous scenarios, there are a lot of things you have to think about. On the one hand, you always have this trade-off of trying to be really efficient, which for us often relates to using a high degree of autonomy, but also being very robust, especially in space. We usually can't afford to make some small mistake and lose one of our robots. We also have to always think about how dynamic are the situations that we want to interact with. On the one hand, that means the dynamic environments. Maybe we don't know exactly what the environment is going to be like, that our robots have to act in autonomously, but potentially also objectives. So if we're doing a scientific long-term traverse, maybe we want our robots to autonomously think about what interesting scientific goals might be while they're doing that. And also quite important, something we focus on significantly, is if we don't only have one robot, but multiple robots, we really have to think about how they can cooperate efficiently and in a useful manner. So to give you some background, I'm really not going to go into a lot of detail about the robotic sides, but give you some overview. Like if we are doing an autonomous control architecture, usually we have, on the one hand, the actual execution. Built on top of that, we have some type of action planning, which for example, plans navigation trajectories or robot arm movements. On top of that, we have some form of task planning that thinks about how to actually complete a more complicated task using these different actions we have. And potentially another layer on top of that is the actual planning of how to turn potential goals I want to do into actionable tasks, so the actual mission planning itself. Realistically, there's always going to be an operator involved in there somehow. Oh, and we're going to wait till this slide. Yeah, okay, there it is. But what this operator does changes a lot on the actual application. In many current, especially space robotics use cases, I would at least argue that the operator gives a very detailed plan that's then executed and supervised by the robot. But there are also applications where we might control the robot via these higher level actions or on these task space. So all of these are different interfaces that we can use to control the robot. The difference basically is, does the operator say, move this joint of your arm by this amount of degree in this time, or does the operator say, please make a measurement there? And just in case you're interested, how far left do you have to be on this to be called autonomy? In robotics, there's a very handy way to look at that. Whoever the speaker is, what they are doing is called autonomy. And everything that's less autonomous than that is not real autonomy. So what I'm trying to say there is there's a lot of questions about how much high-level planning you actually need to be justified to be called autonomy. Well, let's wait for the slides to catch up. Okay, now they're actually coming along. Okay, but let's go into what we are actually doing, what our approach is to solve this. What we are doing is what we and others call scalable autonomy. The idea is, instead of providing some way to control the robot on one of these levels, we want to be able to do it on all of them at once. So we want to provide all of these interfaces I just talked about, potentially for multiple robots in our robot team use case. And that's quite important, we want to be able to have conflict resolution strategies if we are mixing those command levels together. So if I gave the robot a command like, go explore this area, the robot needs to know what to do when I now suddenly press forward on my joystick, which is quite complicated. Then, using these interfaces, what we are actually doing is we force this autonomy architecture I just talked about to use the same control interfaces our operator is using. This can get quite annoying, but the advantage is this forces our architecture to be very, very modular, which allows us to be quite independent from the actual components. So if I want to, say, switch to the potential field navigation planning that was just mentioned beforehand, I can, in theory, drop this in there quite easily. And then we also include some high-level cooperation functionality for our robots, which means on this mission goal to task planning layer, our robots are able to communicate with each other, exchange their expected strengths and weaknesses and utilities with the different mission goals, and then plan basically together, but without having like a centralized planning instance, which is quite important in space scenarios when you can't guarantee to have constant connection to some big server. So what this creates is, on the one hand, a scalable degree of autonomy, which is where the approach is basically named from. So we can choose the interface we're controlling the robot with as we need in a given situation. So use more manual control when something is very important or risky, and more autonomy when we don't need that. An also important feature of that, especially when developing towards these huge, important autonomous missions, is not everything has to work fully autonomously right away, because we can mix and match these interfaces as needed. And also important for scalability of these mission sizes, this drastically reduces the operator workload and stress compared to like full direct teleoperation of all the robots. We can also quite easily scale the team with this approach. On the one hand, because one operator can, in theory, control many, many robots because they don't need that much help. I put a little asterisk on any because realistically, while we haven't tested it yet, there are some numbers where it doesn't make sense to have a single robot operator anymore. And you can also change the robot team, potentially on the fly, which is especially relevant when robots fail for whatever reason, and we need other robots to take over. And we can also scale this to different new scenarios by just applying new task resolution strategies to our full architecture without reworking all of this. I have a few examples of other applications where we are using this. Right now, this is from basically decontamination and catastrophic assistance scenario, where we're actually inside of a nuclear power plant, doing stuff with our robots somewhat autonomously there. Then I have a traditional industry inspection scenario, where you can see on the one hand an operator level where we are defining a mission on the go, while the robot is mostly autonomously executing that. And going back a little bit more to space, I have an example from a DLR-funded project we just completed called IntelliRisk, where we actually did a full exploration mission in the Tabernas Desert. So doing a really huge area with several robots in a kind of complicated terrain. This is quite harder than it looks like, because the thermodynamics of the ground are pretty difficult there. Finally, I want to quickly go into what we are, one of the things we're doing right now. I mentioned in the beginning, we were able to win the Space Resources Challenge, and the prize was not something boring like money, but a new project. So that's what we're doing right now. We're working together with the Glimpse team from Switzerland as a direct follow-up to basically what we did in the Space Resources Challenge, with the explicit goal to push TRL and the maturity of the technologies there. To give you some inkling of what has happened there so far, we've really gotten into real prospecting scenarios that we could do in the moon, up to designing full robot navigation plans and what resources we want to look at with what instruments. And while we're not going to do that, at least not as part of this project, we're using this to inform which technologies are now actually needed, which technologies do we want to push. And now we are trying to build an analog mission that we actually want to complete by the end of this year to really showcase how mature this technology can get. All of this with more robots and, from our point of view at least, more foreign technologies, because we have to integrate all the stacks of the other team as well. So to summarize, all this scalable multi-robot autonomy approach allows us to very efficiently combine robustness with the autonomy we want, at least in the end, hopefully. And I at least believe that's the most realistic path we have towards real large-scale autonomy, especially in scenarios such as space. We've tested this quite a bit on many different applications. I just gave a very brief overview of what we've done there. But we're always working on more, and maybe to finish with that, if there's anything you're working on where you think this might be interesting for us to have a look at and do a prototype study there, please find me, either later on here or on one of these communication channels on there. And with that, I'm at the end. Thank you very much for your attention.
Thank you very much, Tristan. Very nice talk, very interesting. Let's give the audience the opportunity. I see a hand over there, please. We need a microphone. This direction.
Oh, hello. Am I on? So my name is Shivam. Again, I think already people know. So I've been pursuing my master's in space technologies and business in University of Luxembourg and working in the Space System Engineering Research Group at S&T University of Luxembourg. You mentioned about multi-robots. So I was curious, what type of SLAM algorithms do you guys use for better communication between these robots and making sure that there is also redundancy and no extra coverage of area and things like that. So if you could highlight or dive a little bit deeper into the SLAM algorithm as well.
Yeah, the SLAM we're using as a basis, we're just using cartographer, which I assume is enough for you to know what I'm talking about, which is actually not like a multi-robot SLAM. So our SLAM is single robot, but then we're doing cross-localization between these robots and merging the actual 3D map we're generating on top of cartographer. So we have our own open source 3D mapping framework that we've built on top of Cartographer. And this is what we're using to merge the different robot maps and then doing multi-robot stuff inside of that. If you need more details, I think it's better to find me later on. I could talk for quite a while about that, but I think I will get in trouble.
Okay, and herewith, I think we close the session. We have already slightly overrun, and I don't want to run into trouble with you. So we close here. Thanks again to Tristan.